In this video, I will explain you the concept of radioactivity. Okay. Now, in the previous lectures, I have explained you the curve of binding energy per nucleon. So it was like this. Now, element that has got its mass number more than 170, we have seen that binding energy per nucleon is decreasing. So we will specially take those scenarios where mass number is greater than 170 or the size of the nucleus is higher. So not more than 170, I could take example of about 200, anyway, any element after 170. Okay. So higher the mass number, higher would be radioactivity. So like uranium has got property of radioactivity. So higher is the size of the nucleus, higher would be the radioactivity. So I am taking an example of uranium 238 or 236, any isotope. Okay, uranium 92, 238. So what will happen when 238 numbers of nucleons are packed inside a nucleus? Now see, these nucleons are bind by a nuclear energy that is this much. Anyway, from the graph itself, this nuclear energy is less compared to this. Nuclear energy available per nucleon is less, but here it is more. So we know that this is a less stable nucleus because per nucleon the available nuclear energy or binding energy per nucleon is less. And the reason is when we are packing a lot of nucleons inside a nucleus, then we could say that, see, I am going to explain the stability of these two protons. So these are attracted by all other protons and neutrons which are nearby by strong nuclear force, but whenever the distance is higher, now this is one proton and so this is also another proton, now the distance in between them is higher, so that the strength of nuclear force will become lesser and Coulomb's law of repulsive force will come to the existence. Here also Coulomb's law of repulsion is there, but nuclear force is so strong. Okay, this is the nuclear force, curve of nuclear force. At 0.8 Fermi it is more, then that decreases. Okay, so these are short range force and we know that whenever distance are increased beyond 0.8 Fermi, what will happen? Nuclear force is getting decreased. See, this is actually 0. Okay, so nuclear force is coming towards 0. And after 3 Fermi, that will completely become 0. 3 or 2 Fermi. Okay. Now, so when the size of the nucleus is so high, such a way that the nuclear force in between the farthest nucleons would be less and Coulomb's force of repulsion would be very high. So that now these nucleus are offering repulsive force on this and this will have a tendency to go out. So the whole thing is nucleus. Now from the nucleus, due to the repulsive force, and this is due to multiple factors, due to lower binding energy per nucleons and lower nuclear force and higher Coulomb's law force of repulsion. So considering all these things, we could say that it will have a tendency to emit a particle from nucleus. So this is called as process of decay. Now this emission has happened from where? Inside nucleus. From nucleus these emissions are happening. So in photoelectric effect, there is emission of electron, but that is happening from an atom. From its orbit, emission is taking place, but here in this case, inside nucleus, from the nucleus, these emissions are taken place. So these are called as nuclear emissions. Okay. Now, radioactivity has been defined as spontaneous emission in which there is an emission of particle or energy. So here in this case, I have explained you emission of a particle and there will also be emission of energy, that is nothing but photon from nucleus. Okay. Now this is the reason you can say lower binding energy per nucleon, you can say lower nuclear force or higher Coulomb's force of repulsion. Okay, all these are the factors that give rise to the property radioactivity. Now this decay process, I have told you, either it would be a particle decay or particle would be emitted out or energy would be emitted out. In particle emission we have two different types, that is alpha decay and beta decay. In alpha and beta decay, a particle would be emitted, and in gamma energy would be emitted out. In alpha decay it would be emission of He24 nucleus. Helium nucleus is 2 proton, so 1 proton, another proton, and 4 minus 2, that is 2 neutron. So this is helium nucleus. So from here I could say that 4 members would be going out. Out of this, these 2 are proton, these 2 are neutron. A helium nucleus is emitted out. In the case of beta decay, it is emission of electron or positron. This I will explain in detail in coming lecture. So anyway, it's either emission of electron or positron. You may have a confusion how emission of electron is possible from nucleus, because nucleus doesn't have electron inside it. I will explain it, okay, in the coming lecture. So either electron or positron. Positron is nothing but a charge that is having opposite to the charge of electron. Electron is having negative charge. Opposite to that we have positive charge, and equal in mass to the mass of electron. So if I am saying proton, the problem is mass of proton. Charge is exactly opposite, but the mass here it is heavier. But in the case of positron, mass is same, even charge is same, but it is just the opposite. Okay. Now there is gamma decay. Gamma decay is nothing but an energy is radiated out. So it doesn't have any change in number of nucleons, but it simply emit radiations out. So these are nothing but energy. So for example, after gamma decay, a nucleus would go from higher energy to lower energy because energies are radiated out. So these are decays. These are 3 different decay process. We will go in depth in coming lectures. Now radioactivity. So radioactivity, so higher the radioactivity means higher number of particles would be emitted out in a second, right? So certain particle would be able to have 100 alpha emissions in a second, certain would be able to do only 25 or 50, so 50 alpha emissions or 20 alpha emissions per second. So all these are having the property of radioactivity, but the emission per second is different. So we have to define the rate of radioactivity. Now we give a new law for radioactivity, that is nothing but law of radioactivity. That means rate of decay, that is delta n by delta t. So let's say we have 100 nucleus initially, that is n0, total number of nucleus initially. After 2 seconds, this n0 become 80. So this is n number of nucleus after 2 seconds. So after a time of 2 seconds, number of nucleus from 100 it has become 80, which means 20 number of nucleus has got decayed. Okay. So what is the rate of radioactive decay here? That is 100 minus 80. Actually it is 80 minus 100, but that would be negative. So in the case of decay, I could say that 20 nucleus has got disintegrated, and that happened in 2 seconds. See, 100 minus 80, for this it took 2 seconds. So I can say that 100 minus 80 is 20. 20 by 2, which is 10 disintegration or 10 decays per second. Disintegration per second. Okay. So as per law of radioactivity, rate of decay, that is delta n by delta t, this factor, disintegration per second, is directly proportional to number of nucleus at that time. It means that if you are having 100 nucleus, it will have certain rate of radioactive decay, and if you are having 1000 nucleus, it will have different value, but when the number of nucleus present at that time is larger, rate of decay would be higher. So for 100, if decay is 2 per second, 2 decays per second, then if it is 1000, this would be 20 per second. So higher the number, rate of decay would be higher. So how would we put this in an equation, in a mathematical representation? The equation is rate of disintegration or rate of decay, delta n divided by delta t, delta n divided by delta t is directly proportional to number of nucleus at that time. So that is number of nucleus at that time, n. Okay, now we know one thing, that we can convert a proportionality into equation by multiplying with a constant. So delta n by delta t would be a constant lambda into n, and this lambda is decay constant. Why decay constant? Higher the lambda, higher would be the rate of radioactive decay. Now we know delta n means final minus initial, nt minus n0. In this example, final number of nucleus is 80, initial is 100. So 80 minus 100 would be a negative value, but we need a positive value, right? So I will keep a negative sign here, just to adjust with the sign. If you are taking delta means final minus initial, here it would be 80 minus 100, that will become minus 20, but we have 20 disintegration per second. Just to adjust that, I am keeping a negative sign here. Now, to get number of nucleus present at any moment of time, we need an equation for n. Number of nuclei at a particular time is equal to some equation. This is what we are expecting. How to do that? We have to integrate. So I'll keep n here. So delta n by n is equal to minus lambda into delta t. Now for a small time, delta n by delta t can be considered as dn by dt. For a small time considered, this would be equal to minus lambda n. So when I am considering a small interval of time, this equation, instead of delta n by n, this would be, I will keep dn here, dn divided by n is equal to minus lambda dt, because I need in this format, then only I can integrate. Now I am going to do the experiment from n0 to nt, that is from initial number of nucleus to final number of nucleus, and here from t0 time to t time. Okay, so this would be, what is integral of 1 by x or 1 by n? Log n, right? So log to the base e n, log lower limit is n0, upper limit is nt. This is equal to minus lambda. Integral of dt is t itself. Limits are t0 and t. Now substitute the value. Log upper limit is nt. Log nt minus log n0 is equal to minus lambda t minus 0, which is t itself, minus lambda t. So t0 is nothing but 0th second. So 0 to t the integral is, 0 to t is the integral. So this would be t minus 0 would be t itself. Now log a minus log b. Log a minus log b is equal to log of a divided by b. So this would be log of nt divided by n0 is equal to minus lambda t. Now log to the base, this is e, right? So for nt by n0, nt divided by n0, I can take e here. So this would be e power minus lambda t. Which expression says that log to the base e of x, if it is y, then I can say x is equal to e power y. This relation I have applied here. So nt by n0 is equal to e power minus lambda t. Now from here I am going to take the equation, the next process to here. From here it comes and goes here. Nt by n0 is equal to e power minus lambda t. Nt is equal to n0 into e power minus lambda t. This is a very important relation. Number of nucleus present at any moment of time is equal to number of nucleus present at the time when we have taken the first measurement. So I am starting taking my measurement now. I have calculated total number of nucleus. Now after 5 minutes from now, I am going to find the total number of nucleus present in that sample. So now the value is here. After 5 minutes, I can get the value of nt using this equation, that is equal to n0 initial number of nucleus into e, you know value of e, and minus lambda. Lambda is decay constant and t is, in this experiment it would be 5 minutes. This is a very important relation. You should know the derivation of this equation. Okay, thank you.